In the last video, we went through an overview of aromatic molecules, learning about what features define an aromatic molecule and some of the unique ways that these molecules interact with biological systems. In this video, we describe an introduction to the nomenclature of aromatic molecules, and by the end of this video, you will understand the origin of the name TNT for this molecule known as a classic explosive. Now, how do we go about naming aromatic molecules? Well, there are going to be a variety of common parent names. Remember that the parent names that we looked at for acyclic compounds were the longest carbon chain within the organic molecule. In the case of aromatic molecules, the parent name is still the last part of the name of a molecule. The way that it diverges from prior nomenclature is that the parent name is going to refer to the aromatic ring, plus perhaps some group branching off of that aromatic ring altogether. So the parent names for aromatic molecules that you should be familiar with include benzene, which we looked at in the previous video. That's just a six-membered aromatic ring by itself. That's a possible parent name. Additionally, if we have a benzene ring with a methyl group coming off of it, then that is no longer called benzene, that is called toluene as the parent name of the molecule. So the structure that I have shown here in its entirety would be referred to as toluene. No need to specify there's a methyl branch there. The name toluene implies that the methyl branch is there. Styrene refers to our aromatic ring with a 2-carbon alkene coming off of the aromatic ring somewhere. So here's 1, 2 carbons. Styrene, if you've heard the term polystyrene, polystyrene is a plastic material formed by linking a bunch of styrene units together. Benzoic acid is another parent name that we should be aware of and able to apply. And the name benzoic acid refers to an aromatic ring that has a carbon-oxygen double bond attached, and that carbon is also bonded to an OH group. And we abbreviate this commonly as an aromatic ring with COOH attached to it. And you should be able to interpret anytime you see COOH written, the line angle formula that corresponds to is a carbon-oxygen double bond, and that carbon is bonded to an OH group. And the abbreviated way of writing that, because it's a really common group, is referred to as COOH. And so the name of this molecule as a whole would be benzoic acid, a common food preservative. From there, another parent name that you should be familiar with is referred to as phenol, PHENOL. Phenol is present in low concentrations in throat sprays that have a numbing effect. It's a common antiseptic as well. In high concentrations, phenol can be quite dangerous because it acts as an acid, but it also numbs the skin. So if one were to spill really concentrated phenol on their skin would become numb even though they were getting an acid burn. That's a pretty bad situation to be in. Anisole is another common aromatic molecule that forms one of our parent names. It has an oxygen atom directly bonded to the aromatic ring, followed by a methyl group. So OCH3 there causes this structure as a whole to be referred to as anisole. Aniline, I know the names get kind of cloudy here because they're similar in name. Aniline refers to an aromatic ring with a nitrogen NH2 group attached. So if we have this exact theme here of an aromatic ring with NH2 attached, we refer to that compound as aniline. And then finally, last but not least, we have a compound called benzaldehyde. And benzaldehyde has a carbon directly attached to the aromatic ring. That carbon is bonded to an oxygen by a double bond, and then there's a hydrogen bonded to that carbon as well. And you don't necessarily have to show that hydrogen. It's implied in a line angle formula that is there. I just plugged it in there in this case to make it obvious, but you could omit that and it would still imply that to fill the octet in this line angle formula, there would have to be a hydrogen atom right here. So this structure we refer to as benzaldehyde. And there is an abbreviated way to draw out that group, much like with benzoic acid, how we abbreviated COOH. We abbreviate this branch coming off of benzaldehyde as CHO, and that CHO group is completely synonymous with having that carbon-oxygen double bond there, where the carbon is also bonded to a hydrogen. I'll draw that in explicitly there just to remind us that it exists. So of this group, you should be able to recognize and interpret parents that fill any of the names that I'm highlighting here in pink. So all of these are fair game as parent names for aromatic molecules. We won't come across, for purpose of this course at least, any parent names that go beyond these. These will be the full set of last names or parent names that will correspond to aromatic molecules. So I'm going to leave this up on our screen here for reference. I'm going to zoom out on it, and that will give us a chance to take a closer look at some example problems and talk about some situations we may run into when we start to name aromatic molecules, because typically we won't just have these molecules, no other groups bonded to them whatsoever, but it will instead be a molecule that has an OH group coming off of it, as well as some other groups. So how do we deal with situations like that? Let's break our rules for aromatic nomenclature down step by step by step. The parent name, or the last part of the name of the molecule, is going to be one of the names at the left of the slide. In the case of molecules that exactly match what we see there as the parent name would be the entirety of the molecule. On the other hand, if there's a branch coming off of the ring in addition to what comprises the core of the parent name, then we need to specify that as a branch. So when there are two groups bonded to the ring, then what we need to do is number the ring starting at the ring carbon that gives the parent name. So let's take a look at the example related to this. So drawing out an example here. In this example, we notice that we have our aromatic ring with an OH group bonded to it and this branch over here. Matching that up with one of our parent names, we find that the parent name phenol, PHENOL, corresponds to the molecule, specifically to the six-membered ring and to the OH group coming off of it. So therefore, we can assign the parent name of this molecule as phenol. So I'm going to write that in as the last part of the name here. What we haven't yet accounted for is the branch coming off of phenol, which is this group here. If we refer back to our nomenclature video, we would recognize this is an isopropyl group, where we have a 3-carbon group, and it's the middle carbon, which is the point that connects to the parent of the molecule. And so when we have two groups bonded to the ring, as the rule says, we're going to number the ring starting at the ring carbon that gives the parent name. So we start numbering with position number 1 of the ring being where the OH group branched off. And then there's a caveat to this, because we have two ways we could go around the ring. We could go this way and go 1, 2, 3, 4, 5, and put the isopropyl group of carbon 5, or we could take the shorter route around here, and the isopropyl group would be at carbon 1, 2, it would be at carbon 3. So the correct way to go about doing this is going to be to go forth in naming this. When you number starting at the parent name, you are going to number to give the shortest path to the branch. And so therefore, numbering around brings us to the branch being at carbon number 3 of the ring. So we'd call this 3 isopropyl phenol. Let's do another example to illustrate this topic and this concept. I'm going to go ahead and draw out an example problem here, like so. And we'll go ahead and set it up like this. Now looking at our structure compared to the parent name library that we have there in the upper left-hand corner of the screen, what you will find is that the 6-membered ring plus the CHO group is referred to as benzaldehyde. So let's fill in benzaldehyde. And then from there, we need to name anything that we haven't already incorporated into the parent name. The parent name includes that CHO group and the aromatic ring. What it doesn't include is this group here, which is a 4-carbon group that looks like a T. The way that I remember that is T with 4 carbons stands for T-butyl or tert-butyl. And so we fill that in as our prefix, T-butyl benzaldehyde. And since the tert-butyl group could go at any position around the ring, we have to decide what numerical location it's at so that we can make sure we're specifying this molecule and not something else. We always start by numbering at the carbon that gives the namesake, the parent name, and then we take the shortest pathway around the molecule to get to the branch. Going toward this way or toward this way takes the same distance regardless, and so since it's a tie, you can actually go either way here and you'll come up with the same name one way or the other, which is that we should refer to this as 4-tert-butyl or 4-T-butyl benzaldehyde as the complete IUPAC name for this. Now in this system, we have used numbers to indicate the locations of the branches relative to one another. There is an alternative system that you should be aware of and able to apply as well, which is referred to as the ortho, meta, and para designations. So the terms ortho, which we abbreviate as O, M for meta, and P for para, are going to provide us an alternative to using numbers to specify the relative locations of the branches coming off of aromatic rings. And this applies only when we have 2 branches coming off of an aromatic ring. And when we say 2 branches, I'm referring to the branch that's included in the parent name, such as the OH group and phenol, as being one of those 2 branches. Ortho MetaPara describes the 3 possible orientations of the groups relative to one another on the ring. Let's draw out an aromatic ring skeleton here to illustrate what I mean. So our aromatic ring skeleton. And if the 2 branches coming off, which I will call R and R prime as our generic fillers, so R and R prime, if those are on adjacent carbon atoms, we refer to the structure as being ortho or O. In contrast, if the 2 branches are not on adjacent carbons, but instead we skip a carbon in between, so we have R, and then we skip a carbon, and then we have R prime, we refer to that as meta, or M for short. And then finally, last but not least, the last possible option that doesn't start duplicating other options is to have the aromatic ring with our R group here, and then the R prime group, the other branch coming off directly across from that. And we refer to that situation as being para, or P for short. So in the case of the examples up top, applying the terminology ortho, meta, and para toward those, in cases where we have just 2 branches coming off of the ring, we could have alternatively, and just as accurately, referred to 3-isopropyl phenol as being meta or M-isopropyl phenol. That term is completely synonymous with the term 3-isopropyl phenol, because if you draw out the structure of 3-isopropyl phenol, you'll see that the branches are in this orientation at position 1, skip a carbon, and then the other branch there. Much like the meta here, is there's a branch at one position, skip another, and then there's a branch at this position. So that's what we're looking for, is that 1-3 orientation, where this would be group 1, 2, and 3. So the branches there are at positions 1 and 3. And then in the case of 4-T-butyl benzaldehyde, we can similarly take that and convert the name into this Ortho MetaPara designation. I encourage you to hit pause and make sure for yourself that you're able to do this without my help. So 4-tert-butyl benzaldehyde has groups directly across from one another. That matches the template for para. And so I would call this P-T-butyl or tert-butyl. You could have referred to it as benzaldehyde. And you should be able to apply and recognize that either of these names will refer to exactly the same compound. They are completely synonymous with one another. For purposes of assessments, you should be able to apply the Ortho MetaPara terminology or the numerical locations to indicate what particular structure you are looking at using the full list of parent names that are provided here. You will not be provided these names on assessments, but if it is open note or open book, you would have the opportunity to perhaps look those up as needed. With the knowledge that we've acquired over the last several minutes, we can now take a look at the molecule known as TNT and dissect what the full name of this particular explosive molecule is. If we were to compare the structure of this to our list of parent names, what we would find is that the parent name for an aromatic ring directly connected to a methyl group is called toluene. Toluene, forming the parent name or the last name of this structure, is what the last T in TNT stands for, is the T refers to toluene. Now, where does the rest of it come from? Well, if we were looking at the name of this molecule as a whole, remember that when we're numbering, we number starting from the group that leads to the parent name. So that's going to be number 1 at toluene. The molecule is symmetrical, so it doesn't matter whether we number to the left or the right. So I'm just going to number all the way around of our 6-carbon ring. Now we need to specify in front of the parent name toluene the names and locations of the branches coming off of that parent. And we see that there are branches at position 2, at position 4, and at position 6. And in all 3 cases, those are NO2 branches. NO2 branches are referred to as nitro groups. They are very common branches on aromatic rings. They are also notorious for their explosive properties, hence giving TNT its explosive characteristics. So naming this with each of those 3 groups referred to as nitro groups, and there being 3 of them, we refer to 3 identical groups by the term tri. So this would be tri, T-R-I, nitro, toluene. And I should really have the 2 terms run together because we only separate numbers from letters using dashes. These 2 terms, since there's no numbers that are going to separate them, I should squeeze them closer together. So trinitro toluene, and we specify the numerical location of each of those 3 nitro groups as 2, 4, and 6, following the way that we numbered the structure above, where number 1 always refers to whatever branch was part of the parent name. So 2, 4, 6 trinitrotoluene gives us the TN part of TNT, referring to tri for T, N for nitro, or simply TNT for short, leaving out those numerical locations. But this particular compound with the nitro groups in those positions listed 2, 4, 6 is the exact structure of trinitrotoluene. And based on the information that you have seen throughout this video, you should now be comfortable with naming a variety of aromatic molecules that match any of the parent names that we have seen here and have any type of branch name that we have learned